So today, Shruthi will be talking about knotted balls and embedded spaces.
Hi, it's slightly different from the title on my abstract. My abstract said knotted balls by embedding calculus, but I don't know how much embedding calculus I will actually get into, but we will see a little bit of it in this talk. Yeah, I can start if people are ready. All right, so I'm a geometric topologist, which is, I guess, slightly different from the flavor of talks that we've seen in GROOT so far, but I think it'll be fun. Essentially, I study things like knots, which are smooth embeddings of, say, S1 and S3. I would look at isotopy classes of these embeddings, and I noticed that embeddings, not all embeddings are isotopic to the unknot. So unknot would be just a write x squared plus y squared is 1 and you get a circle. But other knots are not isotopic to the unknot. So that's about S1s embedded in S3. You can ask if they're embedded S2s in S3, and it turns out that all of them isotope to the standard embedding that looks just like this. So you won't see knotted spheres in S3, but you can see knotted spheres in S4. If you just add a codimension to knots, you get knotted spheres, and you have embeddings of S2 to S4 that aren't isotopic to the standard sphere sitting in S4. Okay, what other spheres embed into S4? Well, we can ask if S1s embed into S4, and it turns out that all of these can be smoothly isotoped to the unknot. And that's kind of because any crossing like this, can someone see my mouse if I move it over something?
I don't think.
So if I move my mouse on this knot, do you see it?
Yes.
Yes, it's possible.
Yeah, so if I have this crossing, say, in 4 dimensions, I kind of have an extra dimension to change it. And so any embedding of S1 can be isotoped to the standard unknot in S4. Then comes the question, what about S3s in S4? And that's where we get to a conjecture. We actually do not know. The smooth Schoenflies conjecture for dimension 4 claims that any smoothly embedded S3 and S4 could be isotoped to the standard unknotted S3 in S4. So, I will say that there aren't any knotted S3s and S4, but we don't really know. The Schoenflies conjecture is pretty hard, and no one has a good idea how to prove it, or even if it's true. The funny thing is that the smooth Schoenflies conjecture is true for all other spheres. So Sn-1 and Sn is always smoothly isotoped to a standard one for n bigger than 5 or n less than equal to 3. Just dimension 4 that's sitting unknown.
Can I ask a quick question?
Yeah.
Are any partial results known? Do they all have to be slice, for example?
Slice in what sense? So, well, I guess we do know that if the spheres are topologically flat, then they are topologically isotoped to the standard sphere. So there's results in different categories, but the PL and smooth case is still open.
Okay, thanks.
Yeah. But a question similar to that is if, say, you had balls in S4, can you isotope them to be an unknotted ball? Well, the answer is yes, if you can move the boundary around. But if you keep the boundary fixed, it turns out that we don't know whether there are balls in S4 that are knotted or unknotted. And that's so what I mean is, say you have a standard sphere, S3, S2 in this case, in S4. We have like a standard ball that looks like this, and we have our weird ball that's like that. And the question is if this weird ball can be isotoped into the standard ball. And that will be the subject of my talk today. And this question kind of doesn't come up from nowhere. I guess it's somewhat inspired from the Schoenflies conjecture that I mentioned. If you think about any S3 and B4, you can kind of break it up into two balls. And if we know the answer to that question, if you can say isotope the first ball and the second ball kind of just jointly and get an unknotted S3, then that's kind of hopeful for the Schoenflies conjecture. However, the subject of my talk is that there are in fact knotted balls in S4 if you restrict to isotopies that fix the standard S2. So does anyone have questions so far? I will take that as a no and continue. So how do we think about knotted balls sitting inside S4? So let's do a little kind of just pictures and complements and stuff. So, we had a standard sphere in S4. If we look at a neighborhood of that, that's going to be S2 cross B2, because you're thickening a two-dimensional thing in a four-dimensional space. And whenever I draw pictures, I can't draw in dimension 4, but I'll draw in dimension 3. So think of this circle as S2 and a thickened S2 cross D2. And there's the standard ball in here. It turns out that you can write S4 as S2 cross B2, which is this thickened standard sphere, and then its complement is B3 cross S1. So this is the B3, and you go around S1. So what it turns out is like your weird knotted ball is really sitting inside this B3 cross S1. And you have the boundary of that ball being the standard sphere. So the question for looking for knotted balls in S4 changes to looking at knotted balls in B3 cross S1. And I write that as embedding sub-boundary of B3 and B3 cross S1. The boundary down here is to note that these embeddings kind of fix the boundary into like one of the fibers of B3 cross S1. But I still don't really know how to obtain elements of this. But one strategy is to look at this map from the group of diffeomorphisms of B3 cross S1 that fix the boundary. And from there, you get embeddings of balls in B3 cross S1. And the idea is you take a diffeomorphism, and a diffeomorphism B3 cross S1, it's fixing the boundary. So in particular, it fixes the boundary of the B3 cross point, some fiber in here, and you just look at the image of that ball. And that's another ball in B3 cross S1 that's kind of moved around. But we do need some sort of non-isotopic to the identity diffeomorphisms of B3 cross S1 to have any hope that this ball is knotted itself. So let's think a little more about how we can approach this diffeomorphism group. So here's where it connects to my abstract, where we're going to study this diffeomorphism group by looking at an embedding space of S1 into a 4 manifold. I'm going to demonstrate a map that's from pi1 of embeddings of S1 and S1 cross S3 that maps to diffeomorphisms of B3 cross S1. And kind of the overall concept of this construction is like a circle pushing map. And I don't expect any of you to know what that means.
Do you mind if I ask you a question real quick?
Yeah, sounds good.
So is it right that like a sphere is unknotted if the embedding extends to an embedding of the disk?
Yeah.
Is there a similar thing to show if the embedding of the disk is like unknotted? Is there an analogous thing?
I guess I'm not so sure. In this context, if you're looking at a ball that shows up from a diffeomorphism like this, of V3 cross S1, you can definitely say if this diffeomorphism is isotopic to the identity, this is going to be unknotted. And in fact, this turns out to be an if and only if, barring a small correction. So I guess that's one way to see some sort of analogous statement.
Okay.
But it's not quite the same way as spheres and like Jordan curve-like theorems.
Okay, thank you. Is there like a fiber sequence involving like knotted balls and knotted spheres?
Yeah, in fact, we will get to that at the very end.
Oh,
Of this talk.
sweet.
Yeah, I mean, we will actually kind of write down this map coming from a fiber sequence. But yeah, I guess I would. Most of my talk will be geometric, but at the end we'll kind of tie it all together a little more concretely and algebraically. Yeah. Any other questions? Okay. So what is a circle pushing map? Well, so the idea of a circle pushing map kind of comes from mapping class groups of surfaces and point pushing maps. So what a point pushing map is it's a map from pi1 of any surface. Here, let's say we're having the torus, and it's mapped from pi1 of T2 to pi0 of the diffeomorphisms, so to the mapping class group of the torus minus a small disk removed. So it has one boundary component, and we're looking at isotopy classes of diffeomorphisms that fix this boundary. And the way that works is, so you have an element of fundamental group of a torus, let's call it gamma, and I'm going to construct maps, P sub gamma from the interval to diffeomorphism to the torus. It's not yet diffeomorphism to the torus without with the boundary component, but we'll get there. So say we just pick some curve like this. This is our element of the fundamental group of T2. And we're kind of going to get a path of diffeomorphisms of the torus. So we first fix a disk, some point on this curve, and we fix a disk around it. And we're going to kind of find a diffeomorphism by slightly pushing this disk a little over and dragging all the rest of the surface along with it. So we push it a little in this, not much is changing. If we push it a little more, you see things like this curve are deforming a little. And you push it even more, this orange curve or red curve gets more deformed. And you kind of bring this a whole circle. So you go on this whole path, you push this disk along, and you've pushed the surface along and keep getting diffeomorphisms to the torus. At the very end, the rest of the surface is pretty deformed, but this disk is back where it is again. So you note at the end of this path, you get a diffeomorphism of the torus, except it keeps this boundary component, this whole disk intact, so you can restrict it to the torus with that one boundary component. And you look at this, and it turns out that you can't isotope this back to the identity on this torus with boundary component if you are fixing the boundary. You can't get rid of this weird deformation by fixing the boundary but moving around. So yeah, so we then define this map P that I promised, this map from the fundamental group to the mapping class group. We take an element of the fundamental group and map it to this final path diffeomorphism and restrict it to the torus without its boundary. without a neighborhood of a point. So what have we really done? So we took an element of pi1 of T2. I'm going to think of this pi1 of T2 as pi1 of embeddings of a point in T2. We just took a point and sent it around a loop of embeddings of it in T2. And that mapped to pi naught of the diffeomorphism group of T2 without the neighborhood of that point, while fixing boundary. So that's kind of the analogy we have here. And we have a point here, and that same point gets removed over here. And we'll make the same analogy for S1 cross S3. So here we have pi1 of embeddings of S1 and S1 cross S3. If we kind of follow the same analogy, we have pi naught of diff relative boundary of S1 cross S3, and then we've got to remove a neighborhood of S1 cross a point, because that's where this S1 is being taken, because we need to delete that neighborhood. What is this space? We're taking out a whole circle's worth from S3 cross S1. So if you just looked at one of those fibers, you have S3 and you take out a neighborhood of a point, you're going to get a ball. Because a neighborhood of a point in S3 is also a little tiny ball. And then you cross that with S1 and you get S1 cross B3 over here. And on the left, you get exactly the space we had over here. So what we have obtained is a map from embeddings of S1 in S1 cross S3 and found a diffeomorphism of S1 cross B3 that fixes the boundary.
Does it not matter if the S1 is null homotopic or not?
Yeah, so it actually does. So which is why I've written a 0 down here. The base point of our fundamental group will be the S1 that's just embedded like straight up along the S1 factor of S3. So it's like S1 cross a point.
Okay.
Yeah. So we have kind of obtained a way of understanding diff S1 cross B3 in terms of this pi1 of embedding space. Does anyone have questions right now before I move on to understanding that space? Okay, I have it in part 2. So we're going to try to understand the fundamental group of this embedding space. Yeah, and like the question was asked that we're looking at the connected component where the embedding is isotopic to the identity. So that's the embedding sub-0. What are examples of elements over here? Well, so one of them is what I would call a winding element, where you say you have this circle in S1 cross S3, and you want a loop's worth of embedding to this circle. You kind of spin this around a few times and bring it back to the original spot. But, say a point like this has moved around several times. It's kind of just projecting on the S1 factor. We're just saying that pi1 of embeddings of S1 and S1 has this Z's worth of elements by just taking the circle and then parametrizing your loop by another circle and just kind of multiplying it together. So these kinds of winding elements you can characterize by an invariant W1. So it takes an element that's in pi1 of embeddings of S1 and S1 cross S3, and you project that into the first S1 factor, and you look at the degree of that map. Or in other ways, you kind of track how many times a particular point in S1 moves around the S1 factor. those seem sort of expected elements. We didn't kind of have much to do with the fact that this is a 4-dimensional manifold and you should be able to do a lot more interesting things. But this is nevertheless important. We got out some of our easy elements of this fundamental group. The more interesting elements are kind of coming from embedded tori. So we're going to embed T2 into S1 cross S3. But we're going to think of T2 as S1 times S1. And we're going to embed this torus into S1 cross S3 and then obtain an element of pi1 of embeddings of S1 and S1 cross S3. So say this is our torus. We've embedded in S1 cross S3. I like to think of this, the upward direction as the S1 direction and the horizontal as the S3 direction. And you just have on each fiber, so this is our 0, like the starting of our loop. You kind of move around this torus because we've kind of written the torus as S1 cross S1. Which means we want only certain kinds of embeddings. We definitely want our base point circle to be null homotopic, or not null homotopic, homotopic to the S1 factor. And we also kind of don't want the winding problem from last time, where like if you looked at the trace of one of those points, you don't want it to go all around, you just want it to be null homotopic. So we're looking at embeddings of tori where that S1 wedge S1 is fixed, but then everything else can move around. So for instance, we can get a lot more complicated embedded tori because we have a 4-manifold. So what's going on in this picture is you have the original torus you had over here, except you're taking out a really small disk and then sending it all the way around. And then over here, you're going to kind of knot it up with this arc in 4 dimensions. So what happens is this portion is in the future, or in the direction you can't really see, and which is why that tube does not actually intersect that sphere. And then the tube is in the past. It's kind of like a crossing in for knots, where one is higher than the other at some point, one is, and then over here that strand is lower in like time or height. So we still have a torus, it's just that we've kind of done surgery on this disk to knot up with itself. And so what do our embedded circles look like? Well, all the way here, we're going to get the straight circle. Until we go here, that seems the case, but when we go here, we're going to slightly move along the tube a bit. And then if you kind of go towards the back, you're actually, I'm going to draw it a little parallel, you're going to have a circle that goes all the way around, comes back over here, and links itself, and goes back down there, and joins back with itself. Does that make sense? And you can do that, you can kind of do this process a lot of times. You can have this tube going around several times around your S1 factor and then knotting up. You can have perhaps more knotted up spheres with your arcs as well, and really all sorts of combinations of that. But just for notation, if I have n tubes over here and one sphere linked up to the first tube, I will call that alpha sub n, that embedded tori. So then the question is, can we kind of classify these tori, all the possible tori that exist? And we can. So last time we defined a W1 invariant, which was like a winding number, and W2 is a little more complicated. But essentially it takes an element of, it takes an embedded torus and gives you an element in, it gives you a polynomial of sorts in this group, which is, you have all polynomials with z coefficients, except you have a bunch of relations where t to the 0 is 0, t to the 1 is 0, and that t to the k is equal to t to the negative k. So what that really means is, so like if t1 is 0, then t to the negative 1 is also 0. So we just have generators, so you have polynomials that are some z times t squared plus something else times t cubed plus blah, blah, blah. And we're going to get, so W2 gives us an invariant in this polynomial ring.
I'm confused. If t to the k equals t to the negative k, doesn't that mean t to the 2k is?
Right. So I guess we shouldn't be thinking of it as a ring. We just look at it as a abelian group generated by these powers of t with relations on this abelian group.
Okay.
Yeah. So it does not have a ring structure here. Because like this is like a fundamental group, so we don't expect a ring structure per se. So nothing like nothing like that happens. That we don't get that everything is trivial. We do get elements like 3t squared plus blah blah blah.
Okay.
I'm not actually going to define this invariant, but I will give you an idea of what's happening. So W2 is written as a sum over, so you're going to have a summation of some t to the k's, and you're summing over alignments of points. What I mean by that is when you look at your embedded torus and you see 2 points on your torus that has the same projection onto S3 but different S1 values, you're going to sum over situations like that. So in fact, it's like written in terms of like a configuration space invariant, and you're intersecting a couple of configuration spaces. But I will tell you what these invariants, their values on these tori that I drew over here. We have, say, for alpha 1, let me take out this extraneous diagram. You kind of see that somewhere in this knotting process, there's going to be a time where you're forced to have one point of this torus directly over another point of this torus. And so for alpha 1, if you have like one tube like this, your invariant is going to be t squared minus t to the 0. But in this system, t to the 0 was 0, so we just get t squared. Alpha 2 is when you have 2 tubes, you get t to the 3 minus t to the 1, but t to the 1 is also 0, so we just get t cubed. And for alpha n, when you have n tubes, you will get t to the n plus 1 minus t to the n minus 1. And so, so what Gabay and Budney proved as recently as last year, a few months ago, is that pi 1 of embeddings of S1 and S1 cross S3 is completely characterized by this W1 and W2. That all the possible invariants are the spinning ones or these embedded tori and combinations of those. So this group is in fact is Z plus direct sum with this weird polynomial group. I will give a very short sketch of how it's proved. So the first thing that they do is show that this is an epimorphism. So you want to say that all these W1 and W2 invariants are realized. We know that all the W1 invariants are realized. You just spin n times and you get n. For W2, you can kind of look at it from these invariants that it's quite actually simple to compute once you know the definition of W2. You have T2 and T3, and if you just need T4, and you would get from alpha 4, so that would be T4 minus T2, and since you've already got that, then you obtain T4, and so you get all the generators that you need. But yeah, the work in this is mostly showing something like W2 is actual invariant, where you have to kind of carefully deal with configuration spaces and compactified stuff and homotopies on that. And the second part is showing it's an isomorphism is actually more complicated. And this is where they use embedding calculus. I believe there was an embedding calculus talk in the past, but if anyone would like a quick 5-minute review, just let me know. I think I have plenty of time.
Yeah, I'd love to.
Okay, let me just get a blank page. So a quick 5-minute summary of embedding calculus is, say, if you have an embedding space of one manifold into another, and you want, there's some condition on the dimensions of these. The idea is you, instead, to find homotopy groups of this space, so you want pi n of this, and that's kind of hard in general, but the idea of Goodwillie and many others since then is to find more approachable spaces. So I guess you have, they call it Taylor approximations of your embedding space, where you have these, you have maps from embeddings to Tn. Let's call this Fn, and Fn will be some an plus b connected. So A is usually not 0 if, like, as A is not 0 as long as n comma m is not 1, 3. So for instance, in our situation, we're looking where n was S1 and m was S1 cross S3. So A will not be 0. So if you go on further, higher and higher n, you get better and better approximations of your homotopy groups of an embedding space. And there's, I guess, some models of what this Tn are. So there's one, often you might see definitions of Tn as a homotopy limit of like some diagram with cubes, and you, for instance, you look at, if n is a 1 manifold, you kind of look at punctured 1 manifolds and try to map it into M, and look at homotopy limits of spaces like that. But there are also other models that are more tractable to do something like this. So if you say you have Tn of embedding of an interval into some manifold M, Dave Sinha has some models that say that this is homotopy equivalent to a mapping space of a certain configuration spaces. So it's a set of maps of, say, Cn of your interval. You have to do some compactification. Then you have Cn of your manifold. So Cn is here is the configuration space of points. So it's just the space of n points in your manifold where no two are the same. And he has certain conditions that these are aligned, sigma n equivariant, and strata preserving. Turns out I can't seem to write. Like, can everyone hear me? It seems like my computer's stuck.
Yep, can hear you.
I'm not able to move anything around.
Okay. Do you want to try stopping the share? Can you do that, or is that frozen as well?
I think that's frozen as well. If you could maybe stop. Okay, I will avoid writing on my screen. I think that might occasionally crash the app and into my whole computer. So, so the idea of embedding calculus essentially is to convert the question of a homotopy group of an embedding space into a homotopy group of a space that you have more idea of, and often you have nice models of this T sub n for your embedding spaces. After that very brief introduction to embedding calculus, we'll see how that shows up in our question. So we need to look at pi1 of embeddings of S1 and S1 cross S3, and they look at pi1 of the second Taylor approximation, and it turns out that this will be one connected, so the pi1 will match. And then they show that T2, which is usually defined as a homotopy limit, at least for the purposes of pi1, is going to be simply looking at maps from C2 of S1 into C2 of S1 cross S3. So C2 of S1 is, well, your first point has S1's worth of choices, and your second point, well, it can't be the first one, so you have an interval's worth. So it turns out C2 of S1 is just a cylinder. And you can actually write explicitly what C2 is and kind of just keep track very carefully that boundaries of this go to the right spots of the boundary here, and that these maps are sigma 2 equivariant. So you have an action of sigma 2 on these configuration spaces. We just swap the order of the points, and you want to preserve that as well. And they do that and kind of compute that pi1 of these set of maps is determined by like the winding number, and then they lift it to a universal to a covering space, and they also show that the only possible fundamental group elements are the ones that you get from W2. And in fact, these are not just specific to S1 and S1 cross S3. You can understand other homotopy groups of embedding spaces of S1 and S1 cross Sn as well, using this same strategy, and they do that as well in this paper. But like I promised, we have a few minutes to talk about like sort of looking at this from like fiber exact sequences and stuff like that. So really our question was studying diffeomorphisms of S1 cross B3, fixing the boundary. And so just for notation, I'm going to say C is S1 cross a point in S1 cross S3 or S1 cross B3 or anything that has S1 cross something in there. So the fiber bundle we're going to look at is, so we have embeddings of S1 and S1 cross 3 as our base. Our total space is diffeomorphisms of S1 cross S3. So we just take a diffeomorphism and then restrict it to S1 cross a point and see where that embeds your circle. Well, what is the fiber? The fiber is essentially the diffeomorphisms that keep that circle fixed. So the fiber here is diffeomorphisms of S1 cross S3 fixing a circle across a point. And then we look at the long exact sequence of homotopy groups. So we have pi1 of diff S1 cross S3, and then we map that to pi1 of embeddings of S1 and S1 cross S3. And that we found to be Z direct sum this polynomial group. And that maps to isotopy classes of diffeomorphisms of S1 cross S3 that fix this circle. This is not quite diffeomorphisms S1 cross B3, but it's definitely connected. If, say, instead of fixing just the circle, you fixed a tubular neighborhood of that, that would give you a diffeomorphism of S1 cross B3. And it turns out that these groups, these diffeomorphism groups are in fact connected, and it's just you have a sort of framing information to add to a diffeomorphism of S1 cross B3 to get the entire group for S1 cross S3 when you fix the circle. And so stated in these terms, what you have is that Gabay and Budney, and I say 2019, 2020 because right now the proof in their archive paper is under reconstruction, but they're on the fix. So probably soon they will have another archive version up showing this. So what they do is in this long exact sequence, they show that this map is on the Z factor. So the idea is you can get any winding number by just taking a yeah, you can get any winding number by a diffeomorphism of S1 cross S3, a pi1 of that. So you just do the spinning operation on S1 cross S3. And that gives you the pi1 elements that come from winding around. And so essentially what they show in their theorem is that W2 invariant of this image is 0. So all of the W2 invariants map into this group here. And with a little careful checking, they show that it does not go into any of this framing part and goes directly into pi naught diff of S1 cross B3. And going from there to embedded balls also happens fine. They show that this diffeomorphism of S1 cross B3 is homotopy equivalent to our embedding space in question, so balls in B3 cross S1, times a small correction factor, which is diffeomorphisms of a 4-ball fixed boundary. So essentially, if you looked at S1 cross B3 and you removed a B3, you're left with B4. And so any diffeomorphism that is different on that B4 will still give you the same embedding of a ball. But they also work out how to show that this lambda 1,3 maps straight into our embeddings of balls into B3 cross S1. And yeah, so that is their theorem, and they find knotted balls in B3 cross S1, so that means they find knotted balls in S4. And I will stop there. And stop for questions.
Do we know what diff B4 is? Like any
So,
like
so diff B4, this is what you asked for diff B4?
yeah. Do we know like
well, we don't know if it's what its pi 0 is, but there's a recent paper by Watanabe that shows that this is not contractible. So in fact, that there's an element of pi 1 of diff B4. So it's not very simple as a space. So that's actually quite interesting as a question. Yeah.
okay. Yeah, separate question is the W1 and the W2 invariants. Is the W1 kind of a linear invariant and W2 a quadratic?
Yeah, so we can also see W. So when I mentioned that this can be generalized for embeddings of S1 and S1 cross Sn, the W1 invariant is, like you said, linear, and W2 is just the next invariant that's not the same, not the same homotopy group as just maps of S1 into S1 cross Sn. It turns out that the n-2 homotopy group will not be trivial for this, but it'll be trivial for maps S1 into S1 cross Sn.
Okay. Thanks.
So in general, I'm not super familiar with the types of proofs that go into these arguments. Was there something new and surprising in this proof, or are most of the ingredients here things you typically see?
I guess from my perspective as a geometric topologist, the construction of these knotted balls coming from, like, it wasn't quite clear how to look at diffeomorphisms of S1 cross B3, and this circle pushing kind of works. So that's, I guess, interesting. Other than that, I think it's somewhat routine for like this fiber bundle stuff. The invariant W2 is definitely useful. And I think there's work on pi 1 of embeddings of S1 and S1 cross S3 before that said there's like a infinitely generated group, but they didn't know much about what it is. So that is something that they did new.
Okay, cool. Yeah, it's neat that you can write that down, or that they've written that down.
Yeah.
Any other questions?
I had a quick question. So I'm really not in this field, but I thought it was cool seeing this explicit realization of from Dave Sinha on like the embedding on the Taylor Tower, the stage of the Taylor Tower for embedding.
So I don't think they exactly use Dev's mapping space model, but it seems to sort of be similar. So Dev's model is for embeddings of the interval into some manifold. And I don't think it was exactly clear to the authors how to convert that for the S1 case, but it turns out at least for T2, it's sort of similar to that model. So I guess there's some expectation that higher Taylor approximations might also be similar to Dave's model.
Yeah, I thought that was cool. Maybe it's not completely to him, but I thought it was cool seeing that and seeing that being used here. Now, another question from someone that's not really in this area, but like, have you thought about using these results and putting it into the heterospectral sequence to
Sorry, I
Okay.
could not hear the last.
Like, have you thought about like this information about the homotopy groups of these embeddings or like this different Morrison spaces are to like their inputs for the heterospectral sequence that tell you like the A theory of stuff. Like, have you thought about like?
I haven't thought about that, but that sounds interesting. Yeah.
Okay.
Yeah. Thanks.
Yeah, thanks.
Any other questions? Okay, well, on behalf of everyone, I'd like to thank Shruthi again.
Thanks for listening.
Yeah, thanks. It was a great talk.